here. And hopefully you've had a good weekend and we're ready to start. Like I said, we are starting a new unit. We're going to talk about the physical properties of solutions. So let's go there right away and start doing this. Make sure I get my notes. And as a matter of fact, my own notes are a little messed up. So hopefully I don't get you off track here. All right. So we're going to start out by reviewing a few things about solutions. First of all, a solution is a homogeneous mixture. Remember what homogeneous means, right? You cannot tell the components apart. Of two or more substances. Now we're going to add something here that we hadn't added before, with specific intermolecular forces. When we had our first round, I think it was back in Unit 4, we talked about solutions, we didn't include this component. And so any homogeneous mixture was a solution for us back then. But as we will see over the next couple of lectures, there's some caveats, some little things that we had to fix here. Remember that we say the solute is the substance, or the solutes are the substances present in the smaller amount, and the solvent is the substance present in the larger amount. Sometimes who the solute is and who the solvent is a little arbitrary, particularly when we mix one liquid with another one. But if we consider a typical solution, let's consider a soft drink, since I have the picture in there. Of course, the solvent for this and many other types of solutions will be water. And the solutes here would be different things. In the case of a soft drink, you'd have sugar, you have dissolved carbon dioxide. It gives its little fizz, right? You'd have some artificial flavorings or natural flavorings, depending on the type of soda that it is. Now, in the past, we consider other homogeneous mixtures as if they were also solutions. For example, excuse me, I choked a little bit there. We thought of air as being a solution because it is a homogeneous mixture. And we would say that, well, the solvent would be nitrogen because it's the gas that's present in a larger amount. And then oxygen, methane, argon, carbon dioxide, even, water vapor might be considered as the solutes. Excuse me. However, the reason why we might not consider air to be a solution is because, as we know, gases by definition do not have any intermolecular force attractions between them. And so on that basis, we would not consider air to be a solution. It was simply a homogeneous mixture. In the same way, we might consider an alloy such as brass. We might consider it a solution or simply a homogeneous mixture. We wouldn't know unless we knew exactly what kinds of interactions are present between the components. Brass is mainly made of copper metal, but it has other types of metals in there, for example, zinc, sometimes chromium, sometimes even other things. So the idea is that going forward, we're going to think of solutions as a homogeneous mixture where there is some kind of intermolecular force connecting the solute or solutes with the solvent. The other types of homogeneous mixtures might fall under other categories that you'll study on your own in the textbook. For example, colloids, suspensions, gels, things like that. So you'll be studying that on your own, but I wanted to point that out because the main subject of our next lecture, maybe not today, will be the intermolecular forces that are present between a solute and solvent. Okay, let's go through some set of definitions here. First of all, when the solvent is water, remember we call that an aqueous solution. And when we studied reactions in aqueous solutions, remember we used the symbol parenthesis AQ to indicate the reactant or product being a solute in an aqueous solution. Okay, now we can dissolve all kinds of amounts of a solute in the solvent as long as they will dissolve. At some point, you reach the maximum amount of solute that will dissolve in a given amount of solvent at a specific temperature, and we'll call that a saturated solution. It's the maximum amount of solute that you can put in there at that temperature. That means that any solution that has less solute than the solvent has the capacity to dissolve at that specific temperature, we're going to call that an unsaturated solution. And of course, this is a mainly qualitative description because, as we know from the past, you can have many different concentrations of solute. So anything below the saturation level will be considered unsaturated. Now, one trick you can do is, because dissolving something in a solvent is sensitive to temperature, you can actually dissolve typically more solute at a higher temperature. And if you bring the temperature down very, very slowly, very carefully, you might end up where the solute remains dissolved, even though at the lower temperature, it should have actually fallen out of solution. We call that a supersaturated solution. It contains more solute than should be present in a saturated solution at that specific temperature. And you can do some really interesting things, for example, with sodium acetate crystals. If we were in the real classroom, I would have brought out some of this stuff to show you in real life. But on the left there, you see a flask that has a supersaturated solution of sodium acetate. If you drop a little tiny seed crystal into that supersaturated solution, what you see is that it nucleates a process, and you can see in the middle, crystals are starting to form until on the right side, you can see how all of the excess sodium acetate that was in that supersaturated solution essentially crystallized. Beautiful crystals. You can sometimes achieve this by simply putting in a glass rod and scratching the inside surface of the flask. That by itself might nucleate the process of having these sodium acetate crystals form in here inside this flask. All right. Now, when you look at this process, it might remind you of something we studied in the past, which was precipitation reactions. Now, typically, for the most part, there are several differences between precipitation and crystallization. Of course, both of them refer to a solid becoming insoluble due to a change in conditions. Now, precipitates and crystals are different in appearance. Precipitates are typically made of small particles of undefined shape, whereas crystals are made of large, well-formed particles. And of course, we talked about, crystalline solids in the previous unit, so that's where we're headed for. The other thing is that typically precipitates are formed by a chemical process. Remember, we talked about combining two solutions that generate an insoluble product. And so typically precipitation is more, for the most part, usually a chemical process, whereas crystallization typically is achieved by a physical process from a supersaturated solution. All right, so those are the main differences. Another thing that we learned in looking at solutions is that what happens when you form a solution, how do you represent it chemically? Well, the chemical representation might be different depending on whether the solute is an ionic or a molecular compound. Remember that ionic compounds, when dissolved, let's say in water, they dissociate, right? The ions separate. And in this case, for sodium chloride, they separate in a 1-to-1 ratio. Remember though, some ionic compounds, the formula unit doesn't consist of 1-to-1 ratios of ions. For example, if this were magnesium chloride, you would have 2 chloride ions for every magnesium ion, and that ratio is maintained in the solution. For molecular compounds that are non-electrolytes, like in this case, I'm showing this would be glucose, C6H12O6. When you dissolve them in water, all that changes is the physical state. Notice the change from S to AQ. But notice that the molecules remain in their integral form without any dissociation or breaking down. An exception to this would be, of course, acids and bases that are molecular, but when they are put in water, they might ionize. Okay, today's lecture is all about concentration. Some of this is going to be review from things that we've done in the past, because I really want you to have that very solidly under, in your hands there. But we're also going to introduce other ways of measuring concentration that we might not have seen before. So we can describe concentration, solutions quantitatively by describing the concentration. Again, let's say that concentration is a way of describing the relative amounts of solute and solvent, right? We already said a saturated solution would have the maximum amount of solute in a given amount of solvent. And of course, we said we have to qualify that. It's at a specific temperature, because this property of dissolving in a solvent is temperature sensitive. An unsaturated solution, as we said, has less solute than a saturated solution. And of course, in the past, when we talk about unsaturated solutions, we can talk about a dilute versus a concentrated solution, which is more of a relative terminology, and actually not really quantitative, but qualitative. So less solute is more dilute, more solute would be more concentrated. So what we like to do is to have a quantitative way of describing this, and that really is what concentration is. When we speak of the concentration of a solution, we want to have some kind of a quantitative, a measured description here, okay? This will be a quantitative property. Okay, let's look at some concentration units that we can use, some of which we have used in the past, some of which we might not have applied specifically. So again, when describing a solution, the concentration is the amount of solute present in a given quantity of solvent or of total solution. So we have to be careful with that last part of the definition, all right? Some concentration units are a ratio of solute to solvent. Some of them are a ratio of solute to total solution. One of the most common ones is the percent by mass. This is used very commonly in many different applications. And the percent by mass, you calculate it by dividing the mass of solute by the total mass of solution, which is solute plus solvent, times 100%, all right? So it's a ratio of solute to solution times 100%. Typically, we call it percent by mass. There's other ways of referring to it. Some authors will refer to it as the percent mass. Sometimes you have the longer version, which is the percent composition by mass. If you remember, in the beginning of the semester, we did an experiment where we analyzed a mixture, and we used the percent by mass to describe that mixture. It was a mixture of, I believe, calcium oxide and calcium carbonate. And I think that that may have been one of the few labs we actually got to do in the lab physically before we went to remote instruction. So this is essentially the same formula. Remember that a solution, is a homogeneous mixture, so it doesn't really have to always be simply an aqueous solution. Another form of describing concentration is the mole fraction. And we use a capital letter X to define it. And it is, like the word or the phrase suggests, it's a ratio of moles. So whereas percent by mass is a ratio of mass of solute to mass of solution, the mole fraction is a ratio of moles of a particular solute A to all the moles of all the components in here. So basically, it's a ratio of moles. We don't typically use percent, although I've sometimes seen it called the mole percent. So all you do basically is same calculation, moles of A divided by the sum of all the moles, but this time you would multiply times 100% to turn it into a percentage. All right. Okay, so let's look at a application of this. Let's do a little practice problem here. All right. If I can get my PowerPoint to move. Oh, here we go. So what is the percent by mass concentration of acetic acid? There's the formula for it. In a vinegar solution that contains 2.70 grams of acetic acid and 122.8 grams of water. Hopefully you get the idea here that vinegar essentially is a solution of acetic acid in water. And depending on the source or the type, you have other components in the final product you buy off the shelf. So you have, apple cider vinegar, you have white vinegar, you might have some kind of like a balsamic vinaigrette kind of thing. There's all kinds of vinegars out there, and they all differ in both the other ingredients that are present, but also in the percent of acetic acid. But when you look at a bottle of vinegar, you might find the percent acetic acid in it. And this is what it is. So remember that the formula here is grams of solute divided by grams of solution times 100%. Don't forget, in applying sig figs, the times 100% has no bearing on it. That's just a way of moving the decimal period. So whatever grams they give you, that's where your sig figs are going to be coming from. All right. So we have 2.70 grams of acetic acid. The solution is not 122.8. That's just the solvent. It's 122.8 plus the acetic acid. So that means that the percent by mass would be grams of solute divided by grams of solution times 100%. You can see where there's going to be 3 sig figs on the top. There's going to be like 4 in the bottom. So to 3 sig figs, this would be 2.15%. So this is a little on the low side. A lot of vinegar solutions from on the shelf, they're like more like towards the 3-4% range. But this is how you calculate it, okay? All right, let's do this. Let's go look at another friend of ours, and that is the molarity. Remember, capital M? Molarity is a little different because in molarity, we relate ratios of different things. It's the moles of solute to the liters of solution. In other words, the units on the top and the bottom are not the same as they are when we do percentages. Now, let me introduce a new unit that perhaps we haven't discussed before. And again, a bit of a tongue twister here. It's called the molality. And we write it with a small m instead of a uppercase M. And this is the moles of solute per mass of solvent in kilograms. Notice the difference. Molarity is a ratio of solute to the volume of the solution. Molality is a ratio of the moles of solute to the kilograms of solvent. So very different units, but please don't get them mixed up, okay? So remember, if something is, let's say, 1 molar, capital M, it would mean it has 1 mole of solute per liter of solution. If something is 1 molal, small m, that means it has 1 mole of solute per kilogram of solvent, not of solution. Now, we all remember the way that we make a solution of a target molarity, right? I hope. We use a special instrument called a volumetric flask. So let's say I want to make a 1 molar solution of sodium chloride in a 1 liter volumetric flask. Remember, first I weighed out the number of grams that make up 1 mole, which for sodium chloride is 58.44 grams. I pour them in. Then I add some water and use the bulb shape of the flask to stir it, to swirl it, and dissolve the solid. And once I've done that, I very carefully add water until I reach the mark on the neck of the flask that indicates that is the volume that this flask is calibrated for, exactly 1 liter. And now you can cover the flask with a, you know, uh, either a piece of plastic film or a stopper if we have the right size. Finish mixing it, and now you have a 1.00 molar solution of NaCl. Of course, we discussed previously that we can also do it by dilution, and I forgot to put the slides for that one in here, but it is going to be in your practice exercises. Speaking of which, this is the slide that I added. And of course, you notice that some of the previous slides were probably out of order compared to the original version of the PowerPoint notes. Here are 3 exercises that have to do with making solutions of known molarity. So if you were able to download the new set of PowerPoint notes, you will have this slide in there. If not, I suggest maybe you can take a screenshot or a picture of it, or maybe just write down these things here. It's a good practice. We're not going to do it all here. I thought maybe we'd do the top one just for practice sake. What do you guys think about that? Okay, let's go ahead and switch over here to my, oops, I think I lost my screen. I think I pushed the wrong button here, but let's see if I can find my, this guy's not working at all. Okay, there we go. So this is the slide we were just doing here. So if you guys want, we can do the first one here for practice and you guys can work on it. And we'll take a break after this. All right, you know what? I'm gonna be doing this with you because I just put these problems in here for you to practice and I haven't actually solved them. So let's go ahead and do it together, all right? How many grams of potassium carbonate are needed to make 280 milliliters of a 2.5 molar solution? You know what? If I had built this problem, I would have set this up with a little dot in there just to make sure it's exactly 280. And I would have probably made this 2.50 molar solution, but I guess it's fine. I mean, my point is that, you know, they never tell you what the objective is when you're making these solutions, and it all depends. I like to think that I want to make it as exact as possible, but okay, let's play with what they have here. Let's play with without the dot here and without the extra 0 here. So that means we're going for 2 sig figs only. Okay, so what do we need here? First of all, that's right, dimensional analysis, right? So I want 280 milliliters of a 2.5 molar solution. So let's start out with that. What does 2.5 molar mean? It means that I'm going to put 2.5, well, actually, you said that's just 2.5, right? Moles in 1 liter, but it's the same as in 1,000 milliliters. And I'm going to be making 280 milliliters. So I'll cancel that out. And they're asking, well, how many grams of potassium carbonate do I need? Well, if I want moles to cancel out, I need moles in the bottom here. So what's missing? That's right. What we're missing is the molar mass of potassium carbonate. Oh, wait a minute, but I need to know what potassium carbonate is, right? So I got to look it up. I know potassium is K. So if that's the metal, that means that the rest of it must have been the, the non-metal anion. And carbonate doesn't sound like an element derivative, so it must be a polyatomic ion. So I gotta go back to those tables that I did in the beginning and find out what it is. It turns out it's CO3. But since potassium is +1, it turns out that carbonate is -2. So if we do the crossover, that means that this is our formula, K2CO3. Right? So I had to find potassium, carbon, 3 oxygens, 2 potassiums. That actually comes out to be 138.21 grams per mole. And now I can cancel out the moles, and I'm going to have the answer in grams. So let's see what that is. So what did we say? 2.5 divided by 1,000 times 280 times 138.21. And the total is 96.747. But remember, the way they gave us the problem, we only had 2 sig figs to play with. So we need to round that, therefore, to 2 sig figs. So that'll be 97 grams. All right. So the next question is, well, now they're going to ask us, if I have 75 grams of lithium bromide, how many liters of 4.00 molar can I make? The third one is finding concentration. I'm going to leave it here. We're going to take a 10-minute break, but I'm going to leave this up here for you guys to play with if you guys want to work on it during the break, or if not, just write it down and you can do it later for practice. I'm doing this just so that we can get sharp again on working with A, dimensional analysis, B, calculating molarities, okay?